Alrighty, let's go ahead and get started with these intro to energy notes. So first thing we want to do is define energy. And energy is the ability to do work on an object. Some of you might be saying to yourselves, that makes sense, right? Energy is the ability to do work. So does that mean when I say, "Oh, Mr. Weiss, I'm so tired. I don't have any energy to do this assignment," that I'm actually correct? Well, technically, yeah. If you don't have any energy, then you don't have the ability to do work. But you and I both know that you do have the energy, so you do have the ability to do work. Let's talk about the 4 different types of energy. The first one I want to talk about is gravitational potential energy. And gravitational potential energy is energy that is stored in an object due to its position in the air. So in other words, it's energy that is related to the height. So how high off the ground is an object? When is it equal to 0? Well, it would be equal to 0 when it's on the ground. Or in other words, when there is no height. The second type of energy I want to talk about is kinetic energy. And kinetic energy is the energy due to motion. So kinetic energy is energy when an object is moving. So when is it equal to 0? When our object is not moving. So in other words, when our object is at rest. The next one is thermal energy. And thermal energy is the energy from friction or air resistance. Another way people define thermal energy is that it is the energy that is lost. So energy that we can't get back. When is that equal to 0? Well, if we're not losing any energy. And we wouldn't lose any if there wasn't any friction or air resistance. There's other ways that we lose energy too, but we're not going to talk about that in this class. An instance of when you can feel thermal energy though, maybe some of you guys experienced this over the summer, is like when you ride your bike and then maybe you come to a stop really quickly. If you were to feel your tires after that, you would notice that your tires are warm. That's a sign of thermal energy. That's energy that went from kinetic because your bike was moving and transferred into thermal energy, that heat on your tires. And that was due to friction. Lastly, we have elastic potential energy. And this is energy that is stored in a spring or a stretchy object. Or your sweatpants, right? Sweatpants have elastic waistbands, so they have elastic potential energy. When is that equal to 0? When it's not stretched, right? So in other words, your sweatpants have no energy when they aren't stretched. That's why you're not scared that they're going to find you in your sleep or anything, right? Because they're not stretched, they have no energy, they can't do anything. I'm sure you guys have seen those videos of people with rubber bands, how they pull the rubber band back and they snap it on their friend. Don't do that, right? That's not cool. But that is an example of elastic potential energy. The further they stretch that rubber band, the more energy it's going to have, meaning the more it's going to hurt that friend when they let go. Let's talk about the law of conservation of energy. Energy is going to be measured in joules. I know you guys have heard of this word before, but in physics, joules is just the unit of energy. The most important thing to know about energy is that it's always conserved. It is physically impossible to create or destroy energy at the moment. There are people, I'm sure, that are working on ways to try to do this, but as far as we know, it is not possible. So when we say you can't create or destroy energy, that means all that we can do is just transfer it. And as we can see in this diagram below, or this GIF or GIF, however you want to pronounce it, we have a roller coaster, right? And this cart is going down, and we see that the potential energy is transferring into kinetic, and then back to potential, and then into kinetic, and then potential, and then back to kinetic, and ending up in potential. What we notice though is that even though potential and kinetic are changing places and some energy is going from one to the other, our total energy is always remaining the same. And that just means, like we said before, that we are not creating or destroying energy, it's just transferring from one form to another. So now that we've talked about the types of energy and showed that energy is just transferred from one to the other, we need a way to show that. And a way to show that with pictures is going to be an energy pie chart. And our goal is going to be to show changes of energies or energy storage as a system undergoes some process. So what we mean by that is that we want to be able to show how energy is moving from one form to another depending on what is happening in that scenario. So for instance, a car is driving down the street and sees a stop sign and stops. The energy is moving from one form when the car is driving to another form when the car is stopping. And just like we said, that would show the conservation of energy throughout that process. So here's our first example, a spring-launched toy that is propelled into the air. Our system has a spring, a toy object, the earth, and the gravitational field. And when we say system, it's really just talking about what are the important pieces of information that we need to know for this scenario. So we can see right here that we have a first point, second point, and third point. The first one is the spring that is compressed. The second point is the spring that is no longer compressed. And the object or the toy is at its maximum height. How do I know it's at its maximum height? Well, the velocity is 0. When is velocity 0 in the air? When we are at our apex. And then the last point is when the object is at its halfway point. So it's at half of the height. So if we look at that first scenario, we see that our toy object is not moving, and we see that the spring is compressed. Because it's not moving, there's no kinetic energy. Because it doesn't have any height, there's no potential energy. And because the spring is compressed, there is elastic potential energy. Therefore, our first pie chart is only elastic potential energy. Let's take a look at our second one. The spring is no longer compressed, so there's no elastic potential energy. The object is not moving, so there's no kinetic energy, but the object is in the air. It has some height. Therefore, it's going to have a gravitational potential energy. And lastly, let's take a look at number 3. So number 3, the spring is not compressed, so there's no elastic potential energy. The object is moving, it's halfway down. Because it's halfway down, that means that we have some height. So we're going to have some gravitational potential energy, and we're also going to have some kinetic. How much of each? Well, it kind of gives it away. It tells us that we're halfway down.
I'm already halfway there. Halfway there. Halfway there.
So that's going to mean that we have half as much gravitational potential energy. So our energy pie chart, half should be GPE and half should be KE. And again, GPE is the energy that comes from height. Our object has half as much height. And KE is the energy that comes from motion, and our object is moving. And again, the reason why we use the pie charts is because our total energy remains the same. So let's quickly recap what we talked about. Types of energy. We got GPE, and that depends on potential energy. We got KE, and that depends on our motion. And then we have EPE, and that depends on a spring, if it's compressed or not compressed. And then also thermal energy, but we can assume that there's no thermal energy unless said otherwise. And we need to remember that energy cannot be created nor destroyed, it's only transferred from one form to another.